G'day, I'm Dan at Woodrow here. We're here at the Outdoor Farm Show with our new innovative soil mapping product and brand called GroundWork. GroundWork is a deep soil sampling methodology that is based on science. We also work with growers to implement agronomic soils-based decision making that helps increase the productivity and profitability on their operations. Why do we think soil type mapping based off of the historical classifications in Ontario is important? And the answer to that is because our soils were formed by glaciers here, and the reality is the soil surveyors of the last 100 years did a fantastic job of giving us really good soil type names and descriptions that relate to production. So what makes GroundWork different than other soil mapping services in the province? Number one is going to be that we're building soil series maps. So you're getting a zone-based map that is based on probabilities, and as such, it's got a higher level of accuracy when compared to other methodologies such as grid sampling. When you're building a script, all of a sudden we can roll it out across an operation, and the decision making a lot more simpler. And we're trying to implement prescription farming or advanced agronomy on yield maps. We're going to have high, low, and average yield zones. When we build and you have a soil type classification map for your field, it allows you to do and make decisions for selective fungicide application, selective insecticide application, variable rate nitrogen, variable rate seeding in both corn, beans, and wheat, as well as variable rate growth rate regulator, because believe it or not, on the label of most growth regulators, it actually says that do not apply to stressed crops, because it can actually set the yield back of wheat in those stressed areas. I think a soil map for your farm that's highly accurate can help increase the ROI, productivity, and profitability on your operation. So up here we have a Brant Fine Sandy Loam. It's a well-drained soil, and we can tell it's well-drained as we look through this soil profile here. The colors are really bright, brown colors, a bit of reddish colors, and there's no indication that the soil has got excess water at all. So it's well to potentially rapidly drain. And the reason for that is we get in the bottom here, we start to see some coarser sands. As we move down to the second member of the Brant Katina here, this is a Tiscola Sandy Loam. So it's again, same material, but as we move down through the soil profile, we notice a few things. We notice that the topsoil's gotten darker, so it's got a higher percentage organic matter than it would if we sent this away for a soil test. And then we start to see kind of some oranginess. And the oranginess here is oxidized iron. And this indicates prominent models, which means that it is in fact an imperfectly drained soil. Water is typically not a limiting factor here, or as big of one throughout the growing season. And then as we move down and we get into the final member of the Brant Katina, this is a Coalwood Sandy Loam, or Coalwood Loam, or Coalwood Silt Loam, depending on what the topsoil is made of. We start to see some really blue-gray glide colors as we get deeper down in the soil profile. So, and really bright orange patches, which is distinct modeling, and this indicates that the soil is in fact poorly drained. So there's lots of water here throughout the growing season, potentially too much unless we manage that water through surface or subsurface drainage. And what we're looking at here is a 3D image of a field. And it's actually a 3D image of the field, because we took the digital elevation model that we built and we hired a 3D printer to build this, so we could show you guys some really cool things. So right now, and just a quick note, this 3D model is exaggerated 7 times. So this field actually is pretty flat overall, right? But we wanted to show you some cool things. So this is the map of organic matter for this field. And as we go through here, you know, in the valleys, we have higher organic matter where there's kind of a concave area, and where we get these convex bumps, right? The organic matter is actually quite a bit lower there. So that's a kind of a quick note about organic matter. But as we were talking about earlier, a soil that's 3% organic matter and 6 inches deep, and a soil that's 3% organic matter but 12 inches deep are going to behave totally differently. So we think it's important if we can take organic matter and times it by topsoil depth, we can get a kind of a total organic matter map that's really representative of the potential to mineralize nutrients. So as we go through this, right, we got these really dark areas here. Nitrogen's not going to be a really big limiting factor here because the soil is producing so much. And crop demand is still going to be high, but because the soil is producing so much, we're going to actually apply a bit less nitrogen here to make the difference between crop demand and supply. Whereas we come up on top of this knoll here, we're going to have, in most years, pretty good yield potential here. Let's say we want a fertilizer for 180 bushel corn. But on the flip side, our potential to mineralize nitrogen and other nutrients is going to be quite significantly less when compared to the high potential soil down here. So this is a map of potassium parts per million on the ammonium acetate test. Red represents high values up to 200 ppm. White represents low values down to 80 ppm of K2O on that test. So if we were going to bulk sample this field, right, we'd come up, or even grid sample this field, the whole field would come up with an average of about 160 parts per million on that ammonium acetate test. But what's really interesting is if we did bulk sample it, we would think we didn't need to fertilize it, when in fact we have a whole significant part of this white area, which is in our highest yielding areas of the field, that if we do not apply higher rates of K2O and increase the potassium test on those soils, potassium is going to be a limiting factor and will limit our crop yields on those soils. If we were to bulk sample this field, we'd end up with a K2O average on the ammonium acetate test of about, or available potassium, of about 160 ppm. That would indicate we do not need to fertilize this field. However, if we looked at all the areas on this map, which is showing the true variability, that actually only represent 160 pounds of K2O, that area is going to represent less than 1% of your field. So if you'd like to learn more about the other 99% of field, go to woodrow.com/groundwork.